Hey, this is Brock Lemires, and in this video I'm going to talk about scaling sine waves using electrical parameters. And specifically I want to talk about how we scale the period of a sine wave using either the frequency or the period of a signal that we have. So we've talked about how sine waves are everywhere in electrical systems, electrical power from generators and also electromagnetic propagating waves. So we use the sine wave to essentially model these. But what we have to do is we have to make the sine wave fit what we actually see in the real world, and then that gives us an accurate model. So if you recall from when you first learned about sine waves, you use this process of scaling and shifting the base sine wave to get it to have the right kind of magnitude and the right frequency and the right phase shift. But when we do this in electrical engineering, we want to use the electrical parameters that we care about. We don't just want to live in a mathematical abstract world. We want to use things that we actually care about. So let's remind ourselves what the parameters are that we care about in electrical engineering. So first and foremost, with respect to time, we care about the period, and we define the period as capital T as the time of one complete cycle. Okay, and that the units are seconds, so we care about that. We also care about frequency, which is the reciprocal of the period, which is simply the number of cycles per second. And that's what we truly care about. And we give that unit, or we give that parameter the unit of hertz after a scientist. And so frequency and period are related by this expression right here. F is equal to 1 over T, or T is equal to 1 over F. But these are the parameters that we talk about in electrical engineering. It's time and it's hertz for frequency, okay? And then, of course, we have phase, which represents how much the sine wave is shifted from t equals 0, okay, from its base, location. And we'll talk about phase in a variety of ways, but it can shift left, it can shift right, but it's with respect to time. So how much time is it shifting left or right? Okay, and then when you look at kind of the y-axis scaling and shifting, what we have is we define the amplitude of the sine wave, or the peak voltage, and that is simply from the center point of the sine wave up to its peak value, and that's what we use when we talk about things. So we say this sine wave has an amplitude of 2 volts. Okay, so that's from the center line to its peak. And then, of course, we also have the offset, which is where the center line of the sine wave is shifted away from the y equals 0 point. Okay. Now, when we do sine wave scaling and shiftings, we aren't talking about RMS, which is root mean square, which is kind of the average number that we use to talk about sine waves. So that RMS doesn't apply to what we're about to talk about. What we're going to talk about is how do you form a sine wave function that uses the parameters that we care about. So let's begin with the time domain scaling. And so what we have with a sine wave is it is defined to complete one cycle in 2 pi. Okay, and what we need to do is figure out how we can make this cycle of a sine wave complete in 1 period. Okay, so we don't want to use 2 pi, we want to use a period. But when you first start looking at this, it helps a lot to try to go back and understand where this 2 pi came from when the sine wave was defined, because it'll kind of remind you how we do this scaling. Okay, so when you start with sine waves, it always goes back to this unit circle. Okay, so this is kind of a review of where this sine wave function came from. So you have this thing called the unit circle. And the unit circle is amazing because it allows us to basically extract cosines and sines from it. And this is used when you try to basically model any periodic wave that has a sine wave function. So some of the things that you start with a unit circle are it has a radius of 1. Okay, and it's centered at coordinates 0, 0. So that means that this coordinate right here would be 1, 0. This coordinate up here would be 0, 1. This coordinate over here would be negative 1, 0. And this coordinate down here would be negative 1. It'd be 0, 0. 0, negative 1. Okay, and so we also defined that you are going to start at this location right here, and you're going to move around the circle this way. So the way this is representing moving around the circle in the counterclockwise measure. And then what we can say is that this is 0 degrees right here, and as we move around the circle, we complete at 360 degrees. And so 0 degrees is equal to 360 degrees. And the reason that this is unbelievable, or this is really cool, is because if you think about it, at any given angle, okay, so let's say we have some angle right here. At any given angle, I can come in here and say, okay, I got an angle, and I can basically look at this and I can take the y value right here, and that is the sine. Okay, and I can also get the cosine as the x value. And if you look at it, if you think about it, they basically represent a sine wave, but not on the time axis. Okay, so if you imagine that we go around the circle, we're going up, then down, up, then down, up, then down, up, then down. Look at the y-axis, what it's doing. You start at y is equal to 0, and then as you move up, as the angle increases, it goes up, and then it goes down, and then it goes up, and then it goes down, and then it goes up, and then it goes down. So this, anytime that you want to know the sine of an angle, you just grab the instantaneous y value, and it gives you that. And so that's why the sine wave is defined between 1 and negative 1. So if you think about the sine wave, it's going up and it's going down. Well, when it's at its peak, it's up here, that's at 1. And then as it goes around and gets down to here, now it's at negative 1. And so these are basically the exact same thing. They're just plotted in a different way. But what's cool about it is that a circle, a unit circle, is exactly gives us the exact wave shape of a sine. And then that's true for a cosine too. If you think about a cosine, so this is the sine, and then this is the cosine. You start at basically the x value. So you're going to start at 1, and you're going to go down and then come back up. And so that's just like the same as going, okay, I'm going to start here, and then as the angle goes around counterclockwise, it goes down to 0, then to negative, then comes back, and it's positive, and it's max, and it's minimum, and then max. So that's kind of this plotting of the cosine right there. Okay, so why did we review that? Well, here is why. When mathematicians came up with the sine wave, they decided that it was better to not use degrees to represent the angle. And instead they came up with something that is called a radian. And so radians and degrees are the same thing. They're angles, okay? So they're angles. We'll just call them angles right here. And I can have radians right here, and then I can have degrees right here, okay? And degrees obviously goes from 0 to 360. Okay, so it's going to go 0 to 360. We all know that. Radians, though, is a little bit different. They define this to be this unitless quantity that actually makes some math work better when you start taking like derivatives of trigonomic functions. And 1 radian, they define 1 radian, okay, is this. Okay, so 1 radian is when you have an angle. Okay, so when you have an angle where the arc length right here is equal to the radius. You have a radius of 1 and you have an arc length of 1. That is called 1 radian. Okay, so, so that is exactly what you have right there. So when 1 radian is 1 arc length is equal to 1 radius. Okay, so it's like, okay, well that's cool. Then the question becomes, how many radians are there in a circle? Okay, and now this is where it's kind of cool. If you've never heard where the constant pi came from, this is where pi comes from. So if you come over here, pi is the ratio. So I'm talking about like pi, like 3.14, is the ratio of the circumference of a circle over its diameter. Okay, and so if you think about it, if you just like took the diameter right there, that little segment, okay, that length, and you laid it down right along the circumference, it'd be like, oh, I got like about 1, and then it's like, here's another one, there's like 3, and then a little bit more. So the circumference divided by the diameter is the constant pi, and that's true for any sized circle. It's like, oh, okay, that's pretty cool. That's where pi comes from. So now the question becomes, how many radians are in a circle? So if we remember, what's the definition of the circumference? Well, it's the circumference of a circle is equal to 2 pi r. Okay, so that's just the equation of a circle. And so what we care about is like, we're trying to know how many radians are in a circumference? Well, let's say divide both sides by r, and what happens is that becomes the number of radians in a circle, and lo and behold, the r's cancel out over here, and you're left with this, 2 pi. So the answer to this is that there are 2 pi radians as you move around the circle. So that is, right here would be 0 radians, okay? And then over here would be 2 pi radians, okay? So here you have it. You got degrees that go from 0 to 360, okay? And that's degrees, and that's the way that our brains think about circles, because that's how we learned about them. And then if you said, oh, no, I'm not using degrees, I'm going to use radians. Those go from 0 to 2 pi, okay? And you can convert back and forth between these. But this is really important because sines are defined using radians, not degrees. And even though your calculator can convert things in degrees and it'll let you put them in an angle, in electrical engineering, we tend to just stick with radians and we scale accordingly. That way you never really have to put your calculator into degree mode. But let's get back to the scaling part of this, okay? So here is where we're ultimately at. We have something that is called sine of something, okay? And that's going to give us our electrical parameter with respect to time. And we want to plug in time. I want time to be a variable here because that's what I care about. I have a sine wave that is varying with time, okay? Because it's modeling some electrical signal. And I want time in there, but I have to apply some sort of scaling factor in order to get it so that it repeats every period, okay? So our time is right here. We want this to be when it repeats. But left by itself, the sine function only takes in 0 to 2 pi before it repeats. So the argument we have to create has to be converted somehow between the period, which is in seconds. We have to convert that over into something that provides the sign, the argument, in a form of 0 to 2 pi. And so what we're trying to do is we're trying to figure out a scaling factor, okay? All right, so how could we do that? Well, here's what we could do. We could say, if you want to take something like a range, okay? So you have this and its base is 2 pi, okay? So you have 2 pi. What I want to do is I could potentially do this. I could say 2 pi, okay? And I could divide it by the period. And if I did that, I would divide this the range of this sine, so 0 to 6, 2 pi, which is 6.28. I divide it by the period, and what that allows me to do is it allows time to march from 0 up to the period. And so then if you think about, like, I'm going to apply time right here. If I multiplied that by time, if I start off at t, okay, t is equal to 0, it's going to be 0 obviously, but it's going to count up until t, but since I'm dividing by t, I basically have this scaling factor that will convert time into something that goes from 0 to 2 pi. So my time can vary from 0 up to the period, whatever that is, and it will then convert that into something that goes from 0 to 2 pi. Okay, so the argument is always going to be something that is within 0 to 6.28 or 0 to 2 pi. And of course, we all know this is going to repeat forever. Okay, but we only care about one cycle because we know it will repeat forever. So this right here is now this scaling factor that allows us to enter time into the sine function and take whatever the scale is for the period. Okay, whatever period we put in there, as long as we multiply it time by 2 pi over the period, it will convert it into something that the sine uses. Well, let's remind ourselves of one other thing. 1 over t, the period, is frequency. So actually we can write this scaling factor as 2 pi f t. And this is it. Okay, so this is what we do in electrical engineering to model a sine wave. We come in here and we say this is going to be, let me rewrite it again, sine of 2 pi frequency multiplied by t. And that right there is how we define it, okay? And that allows us to use frequency given in hertz, okay? And also time, which is time, just marching along. And as long as we apply the scaling factor, it will convert it into something that can be used in the base sine function, which is in radians. Okay, so that is it. That's the scaling factor that we use, and this is pretty awesome. And so then this allows us to kind of come back to this equation that we had right here where we have a plot that goes, if you just plug in t, it goes from 0 to 2 pi before it repeats. Well, now I can start writing it in a more general form, or a more familiar form to electrical engineers, which is v of t is equal to sine 2 pi ft. And that says, if in that form I have scaled the sine wave to repeat, to complete one cycle in period. In one period, and I can plug in t, and when time goes from 0 to t, it will then repeat. And a lot of times in electrical engineering, we leave it in this form. We leave the 2 pi there because it makes it really obvious what our frequency is. So for example, if I came up to you and I just said, hey, I got v of t, okay, and it is equal to sine of 2 pi times 1000 t. And you look at that and you're like, wow, that's a weird way of writing it. Why didn't you multiply this out? And it's like, well, it's because after looking at the way we came up with our scaling factor, I can immediately deduce from that the frequency is 1000 hertz. And I can also know that the period is 1/1000 seconds. So it's very quick to go back to basically interpret what's happening. Okay. So now let's go back. This scaling factor, understanding that, allows us to kind of go back and start defining some of the other things that are of interest to us with this stuff, with respect to sine waves. So let's go back and look at frequency and relate it to this unit circle. Okay, so over here we have frequency. Okay, so let's go frequency. Okay, and we have a hertz. So 1 hertz means it is going to complete in 1 cycle. So that is 1 cycle per second. Okay, and I'll just type out second there. Okay, so 1 hertz is 1 cycle per second. And that's good. But at the same time, we're talking about this other thing, which is called radians. Okay, and so over here, we have this whole thing of like radians. And we're like, well, what if we need to describe frequency in something that uses radians? Well, you can convert back and forth between the two by remembering a couple things. Okay, so this one over here is f. Okay, so we use the lowercase f to say 1 hertz, and it's defined as 1 hertz is 1 cycle per second. You could also say that 1 hertz is equal to 360 degrees per second. Okay, well then in radians, what do you do there? Well, if we equated these things together, what it would be is that you would have to complete 1 cycle in 1 second, which means if you think about it in terms of radians, that's 2 pi per second. Okay, and so you actually have frequency that can be defined in terms of hertz or just regular frequency, or you can define it in terms of radians. And when you do it that way, we call it radian frequency. So it's called the radian frequency. And this is a different thing. It's still frequency. It's cycles per second, but we have to give it another variable or another like symbol. So we give it this dude right here. So this Greek symbol right there. And so this is the lowercase omega. Okay. And so now the question is like, okay, well, I got that and I got that. How do we relate these two? Because I'd like to be able to convert between them. So it turns out like this. If you just wrote what omega is, the angular radian frequency, also called the angular frequency because it's going around a circle. Well, if we try to relate this, basically what you'd say is in radians, if I wanted to convert this into something that I care about, like a period, it would be I would complete 2 pi worth of angle, okay? So that's all the way around here in 1 period. Okay, so that's how I can relate these two things together. So frequencies in terms of seconds, or frequencies in hertz, but frequency is equal to 1/t. So that's how I can put this into something such as time. Well, time is time, right? So then when we look at radians in terms of time and we talk about frequency, it's one circle per how much time? Well, let's relate these two as it takes 1 period to complete, but that's 2 pi radians. And so obviously this can plug into this, and what you end up with is omega is equal to 2 pi f. Okay, and that's how you convert back and forth between hertz and radian frequency or radians per second. And a lot of people, it's technically rad per second, but I don't like saying that. So just say radians per second. Okay, this is pretty sweet. So now we have defined how we scale it. We've actually defined a new thing, which is called radian frequency. And this is what math people use. And sometimes it's easier to use this when you do calculations also. And that's also why you'll see the sine wave written like this a lot of times. So you'll see v of t is equal to sine omega t. And you're like, where in the world did omega come from? Like, why'd you throw that in there? Well, it's trying to relate it back to something that uses time, okay? Because it's not, radians is like this really mathematical thing that's cool and everything, but it's like when you're doing engineering, you need it back into some variable that we care about, which is time. And so this is where the time factor comes into that. So when you do that, that is a scaling factor that allows you to insert the time into the argument of the sine wave. Okay, so to wrap this up, let's look at two quick examples. So what if I gave you this sine wave right here and I said, can you please write an expression for this? And the x-axis is time. So with what we just learned, what I would do is I'd come along here. I notice that it crosses, it's just a traditional sine wave that starts at 0 at time t equals 0. And I come up here and I at one full cycle basically completes at 1.57, hard to get it on there, 1.5725. Okay, so that means my period is equal to 1.5725 seconds. Or I could say that my frequency is equal to what? 1 divided by 1.57. I could say that my frequency is 0.637 hertz. So if I wanted to write that out as an expression, I could come along and I could just say, hey, v of t is equal to sine of 2 pi multiplied by 0.637 hertz multiplied by t. And there you have it. Okay, so that's what the expression would look like. Just to check our work though, let's do this. Let me multiply that all together, even though we sometimes don't do that. So I'm going to take that and I'm going to multiply by 2 pi. So I'm going to go times 2 times pi. And I end up with, that's the same as saying sine of 4t, if I decide to do that. So I come back up into my little Google plot here, and lo and behold, this is sine of 4t. Okay, so it worked. So that actually worked. That's good. Let's do one more of these examples. So I just entered in another sine wave here, and so now this one is much faster. And so I look at this plot and I'm like, write an expression for this. So I come along here and I put my little dot on there, and it is 0.01674. Okay, so I come along and I have my period is equal to 0.016, and we'll call it 61, I guess, seconds. All right, and so you're like, okay, well, there's that expression right there. And then we'll go ahead and pump that into Buddy here, and we'll go 1 divided by 0.01661, and that comes out to be about frequency equals 60 hertz. Okay, so then if I went to write an expression for that, what I would get is I'd say, hey, v of t is equal to sine multiplied by 2 pi times 60 times t. And that's where my frequency would go. And so I'm like, oh, okay, that's pretty awesome. Well, let's check our math really quick. Let's multiply out 60 by 2 pi and see what this actually would be if I just said sine of something times t. So I take that, I go multiply by 2, multiply by pi, and the answer is 378 about. And so if I come in here and I look, what do I have? It is the sine of 377. So almost exactly the same. Okay, so that's it. Perfect. All right, and that turns out that this is actually the expression for the 60 hertz AC signal, AC sine wave that you see coming out of your walls. Okay, that is it. That is scaling sine waves using electrical parameters, and specifically scaling the period. See ya.